Hi, everyone. Thanks for joining us today. We're here to talk about zkOps, the future of zero-knowledge deployment tools. So since zkOps is literally a brand new term that we just defined, I wanted to go ahead and define it for you here today. Fundamentally, we've had a lot of really exciting advances in theoretical zero-knowledge tools. There are new proof systems. We're really excited to see the progress that's been made over the last few years in this area. And there are a lot of very exciting blockchain applications for this new technology. zkOps is about how do you deploy zero knowledge and actually use it at scale. And so this is an engineering problem. This isn't theory. And engineering and theory have always gone hand in hand. And so we figured we need a new term for it just because it's such an operational focus to what we do. Since zero-knowledge proofs rely on a lot of heavy-duty computation, we have custom-designed hardware and software to make zero-knowledge effective at scale. And then there's also a set of integrated software tooling to make this easy to build on. Now, because there's a lot of compute, I want to talk a little bit about Web 2. At this conference, the discussion is that Web 2 is all about centralization and centralized control over systems, and that's true. But Web 2 actually turns out to be a lot of distributed architecture. So when you go to a Facebook, you don't just talk to their server in Menlo Park. You're talking to several different caching layers that are geographically closer to you. And so you can imagine there's a content delivery network with static content close to you. Then you'll have a local data center where there's a database that you interact with. And then that database needs to get replicated back to Menlo Park eventually. And so really this is just a distributed system, but it's controlled by one party. One thing that I think is underappreciated is that the database replication traffic for Facebook is intensive enough that they actually couldn't route it over the internet backbone. They had to lay their own fiber to go between their different data centers because there's that much traffic going between them. And so this is really a distributed system, but it's one where you're being very conscious of where the data is stored, who accesses it, when, and where you locate your compute. So moving to Web 3, we have similar problems in zk, where you have a lot of compute, you'd like it to be near you, and there's lots of data flying around. It's the same type of problem. And so at today's panel, this is what we'll be talking about. Excited to introduce the panel here. So Sevi is a senior cryptographer at Semiotic Labs. Semiotic is a core developer of the graph and has received a $60 million grant from them. At Semiotic, Sevi specializes in using zero-knowledge proofs to upgrade the graph protocol. Prior to Semiotic, he was building secure systems for the US government at Sandia and then at Northrop Grumman. Jules is also a zk engineer. At Alio, he worked on augmenting Marlin with lookup arguments, and at Scroll, he worked on sequencer infrastructure. Jules has also been deeply involved in the supernova recursive snark algorithm and has created an open source implementation that's available on GitHub. Shares, I'm sorry if I'm killing the pronunciation. He is a smart contract developer and backend developer. And he has experience building efficient and secure algorithms, protocols, and smart contracts for several DeFi projects. He previously worked at Paraswap, where he was responsible for developing a significant part of the core aggregation algorithm. Finally, Miko is a managing partner with Gumi Crypto Capital, a $100 million blockchain fund in Silicon Valley. Miko was also the chief developer evangelist for Java at Sun Microsystems and brings deep expertise in developer tooling to our conversation. So with that, let's just start the panel discussion. I've come with some questions today. If you have questions towards the end, happy to take them. Let me just start off kind of basic because this is probably a mixed crowd. Does somebody want to give like an overview of zk tooling today and sort of just what tools you use and when and why? So, are you turned on?
Take that. Is this on?
Check, check.
There we go. Hello. All right. I guess I can take that. Yeah. Yeah, I've worked with a lot of different kinds of tooling over my career. I worked on the Alio cryptography suite. I worked with ArcWorks. I worked with like Bellman, the Zcash crypto stuff.
Cool stuff.
There's a lot of different kinds of tools out there, and the one thing that closer, the one thing that you really notice when you work with a lot of these different crates is that they're very fragmented, right? They're very like vertically integrated, so the all of the infrastructure, all of the curve arithmetic, all that stuff is very like tied to the different crate you're using. So there's no interchangeability anywhere. And that makes it so that the crate that you choose is very context dependent, right? So when I worked on the implementation for the Supernova protocol, originally because I enjoy working with it, I wanted to use the Zcash cryptography suite because it's pretty easy to work with. It's really like easy to reason with. The code's pretty readable, very quick, but I quickly ran into kind of an issue where there's not a lot of extra peripheral gadgets, there's not a lot of infrastructure. I was kind of missing that. So I had to port over to ArcWorks because ArcWorks is one of the most built out libraries out there right now, which meant I had to rewrite almost the entire repository, right? That took me like 2 days. So there's a lot of fragmentation in this ecosystem, and deciding on one thing or the other is pretty difficult because it's such a context dependent choice. Yeah.
I run into exactly the same problems. Like, right, you have to port it was ported to ArcWorks. They got all the curves. You can use this. And like another, just a little point, like with this vertical integration, it's like a lot of these proving systems. It's hard to figure out the actual efficiency and like the actual performance of this proving system, right? Because there's vertical integration, and there's probably a reason for it. Like this proving system is very efficient over this particular curve with this particular field, and so it gets really hard to compare proving systems. So what are you going to use for your particular application and stuff like that too? So, yeah.
Yes. Hello. Yeah. So, I mean, for example, all the zkOps, right? It has such a bad debugging tools. Like, they don't have any. Like, if you want to like write any circuit, you just have to write log statements, right? So it's yeah, we don't really have a lot of tooling to actually develop big systems, like for what we have now.
Hello. Yeah, sorry. Okay, it works. Yeah, I mean, I think we're still super early in tooling, right? And one of the things, so we're actually investors in IronMill, and our thesis around this is that there's always in developer tools, I've been in developer tools since Java, there's always been a dev and an ops, right? And they're not actually the same. DevOps isn't a thing, right? And when you want to say, I'm building an application and I'm scaling it to 1 billion users, right? Like, it's not just like, okay, here's the algorithm, then run, right? Like, it's much, much more involved, right? So, I think we're really excited to see emergent tools like Circum. Like, it's super easy to kind of like for non-ZK researchers to start building circuits. So like, that's great, but like, that's the surface, right? Like, when you actually get to kind of like hyperscale prover infrastructure, that's when you need kind of like big iron, and you need things under the hood like FPGA, ASIC. Like, you just need deep kind of like optimized compute and special purpose compute facility.
Hello. Okay. Okay. Thank you. I guess next question, and since Miko, I know you have another panel that you need to run. This is mostly targeted at you. How do you think about driving adoption of ZK at scale? I mean, what type of tooling do you think needs to be built in the near future so that everybody can start using ZK in their projects?
Yeah. So I think some of this becomes really deep infrastructure, right? So if you look at some core applications, core applications include things like Oracle, right? So there's a bunch of complex Oracle things that are cross-chain verifiers, right? So like, the infrastructure developers are actually kind of okay, right? Like, you're seeing guys on stage here who are basically like, well, we can just rewrite stuff, or we can just go low level and just like freaking do all of it, right? So it's sort of like the tools that make this easy are actually, for the infrastructure side, when you look at applications like ZK Rollup, right? So ZK EVM, when you look at things like ZK Oracle, or when you look at bridging, like, the developers are super sophisticated. So the tooling actually doesn't need to be that sophisticated, right? So I would say that, like, for the other applications, like things like privacy and identity, like we're definitely going to see more things like Circum, right, which actually gives you, like, it's Rust-based, but it gives you sort of a JavaScript interface to sort of build circuits, right? So I feel like this is kind of what we're going to see, I think, next, that will kind of create ease of use.
Cool, awesome. Yeah, so thank you. I want to ask the rest of the panel, it feels like there's a lot of progress in recursive proof algorithms, especially over the last 6-9 months even. And what do you think the future there looks like? Because on one hand, you have recursive proofs that allow tremendous new efficiency gains. On the other hand, it's a recursive proof, so you're generating more proofs. How do you think about like where this is headed, and sort of what do you see as the future end state of recursive proving systems?
Yeah, I'm definitely more of the opinion that we're going more closely towards transparent snark. So something that doesn't require a setup, I think, is just paramount there. I did a lot of work on this at Alio, actually. I helped run the trusted setup ceremony. I wrote a lot of infrastructure to work with the powers that we generated. And on paper, these things are pretty simple. Like, the security is basically the same. You're not really thinking about it, but it's a difficult engineering challenge to work with. You're working with a file of powers that's like 25 gigabytes long. You can naively load that into RAM and work with it, but that's obviously not going to be efficient. That's going to be like terrible for your resource usage. And you're trying to always be more decentralized, so you're thinking about resource constraints, right? So you have to build a lot of extra infrastructure working with the file system. This tends to be unsafe. It's all hassle to deal with, and there's a trade-off obviously between that and using a transparent snark where proofs are like a lot bigger and you have a lot more state load, but there are ways to amortize this. Batching proofs, sort of like that kind of thing. Yeah, I feel like that is definitely the future in that direction. So.
Yeah, I agree. I think it's really interesting. I mean, another kind of like, I feel like, I don't know, standard is popping into my head, but it's not a standard, but like there's a formula that people are using, right, where you can kind of aggregate proofs now, right? So you have a one-step recursion where you have like one proving system, which it proves your big statement, but that's got a big proof, but you want to get that proof up on the EVM, so you want like a small compact proof that can be efficiently proved, so then you hit that. So then you have like a one-step recursion that uses Plonk to basically prove the verification of your big proof and make it efficiently verifiable. So, I mean, it's a cool concept, right? There's a lot of interesting things that I think people can use with this recursion.
Hello? Yeah, so one thing I want to add about like recursive proofs is like these days a lot of papers are claiming to use recursive proofs to like have really high efficiency gains, but it's important that they actually benchmark these, like how much recursions do you need actually, because sometimes they just like say, okay, you can have thousands of like compute machines, but then they don't have any benchmarks in the cost itself. And yeah, like, I mean, I think recursive proofs are very good, especially in blockchain setting, because you have this like incremental model all the places, right? So I think it's going to be very good, but I think we need more concrete benchmarks of like new systems which claim to use recursive proofs for like really high scalability. So yeah, I think, yeah. And also it also relates to Iron Mill, right? When you have like FPGAs and stuff, right, you can really parallelize these things and have these efficiency gains. So, yeah.
Cool. Yeah, thank you. I think on the topic of sort of recursive proofs, and I think the topic of memories come up a few times, one of the interesting things on Web 2 is that we have a lot of resource-constrained nodes, okay, yeah? And yet, even very efficient proving systems, you'd like to have 32 gig of RAM on your node. How do you think about deploying out to smartphones, to IoT, to really the world of the internet, given some of the hardware requirements and especially the memory requirements of proof generation?
Yeah, I think one thing, so I think when snarks first come out, you think okay, we've got a solution. It can just prove, NP statements. This is great. We could just throw this in the circuit. We could kind of prove everything in ZK. And I think what we're learning, right, and especially when we start getting this resource constrained, so we have to get really clever about what specifically do we want to prove as ZK, right? So we want to minimize circuit size. Do we even want to use a circuit? Maybe we want to use a proving system that doesn't require a circuit, right? Maybe we just want to prove this one little thing. If that can be ZK, the rest of our system is fine. So I think a lot of the future is getting really specific about what exactly do we want to prove as ZK versus like just throw the whole thing in a circuit and be done.
It's like thinking about smart contracts, right? Like you don't want to put things on smart contracts. It's very expensive. You want to really find what you exactly want to put on the like trust, like what you want to give out the trust from, right? And then you just put that particular logic in ZK, I guess, to like really, yeah.
I think from the perspective of like really light clients, I think it's pretty interesting. I ran across a project called Kevlar that's like a ultra light client, and it's basically almost like an RPC proxy. And so you're definitely going to see things like that at the edge of the network. Anyhow, sorry, go ahead.
I can add about Kevlar. So I created Kevlar, right? So Kevlar uses something called as proof of stake in sublinear complexity. It's not using zk. That's one of the things where we could build a very efficient light client without even using zk. So one of the arguments about zk is to not use zk in the first place and come up with something better without zk. Yeah.
Cool, thank you. I'm seeing we have about 2 minutes left, so I want to open this to an audience question. Does anybody have something they want to ask? Yes? Here we go.
Hi, I have a question for Michael. Gummy crypto, what do you find that the most exciting for the future's development?
Yeah, so as far as the venture investment community, like the most exciting applications in the ZK area really are cross-chain verification. Like cross-chain verification for things like performance, obviously L2 scalability, right? And then of course the other applications are things like Oracle, like for example, hyper-Oracle type of things, right? Obviously price discovery oracles, maybe like a Lagrange, or like things that kind of really focus on that. Obviously, we're super excited about IronMill, zkOps, and actually like special purpose compute. And then of course, finally bridging, right? Like I'd love to see, and again, that's also cross-chain strong proof. So like we're super happy with that whole class of applications because, you know, we're getting like strong on-chain, cross-chain proofs.
For a smart contract developer who wants to get his feet wet right now on zero-knowledge proofs, what tools would you recommend that have on-chain verifiers?
zkOps for sure. zkOps has, zkOps has definitely, if you write any circuit on zkOps, you can get a smart contract verifier for that. And I think Halo also has it.
Yeah, and then also there's so Plonk. So you see like Plonk, and it's variance. It's got a very efficient verifier on chain. So I think that's why you see such like there's a lot of tools available for that proving system. And so I think like Espresso Systems has a pretty good Plonk ecosystem, and I think they actually have a smart contract implementation too that you can just kind of like take and use that verifier.
All right, I want to thank all of you. I see that we're out of time. I think we'll all be around after the talk if you'd like to ask more questions. Thank you all for coming today, and enjoy the rest of the conference.